All right, there, I heard the beep. I will begin with a word of prayer. Welcome to the visitors. I assume you're visitors, otherwise you're students that have undergone some sort of radical surgery. Seems like a bit much. So that's my son, Daniel. He will hopefully behave better in this class. If you don't want him to misbehave, do not talk to each other and do not use your phones. He's looking for that today. A lot. I will pray. Dear Heavenly Father, we thank you for this day. I pray you'd help us to use this time wisely. That, again, just a little bit more understanding would come from this time for everyone involved, that we'd understand what a series is and when it converges, when it diverges, and maybe why it's interesting, Lord. In your name I pray. Amen. Okay, so talking about the convergence, which I also called yesterday summability. And divergence of a series. Sum n equals 1 to infinity, a sub n, which we can write as a1 plus a2 plus a3 plus ... right? So again, just a warning, reminder, the harmonic series, right? P equals 1 series. We have a sum of terms where the nth term goes to 0, right? So we're adding smaller and smaller and smaller and smaller things, and yet it still diverges, right? So if we find that a sub n goes to 0 as n goes to infinity, that does not tell us that the series converges, right? What does it tell us? Nothing. It tells you nothing. It might converge, it might diverge. You just don't know from this. On the other hand, if we have a sub n does not go to 0 as n goes to infinity, then we do get that the series diverges. This is the so-called nth term test. What other tests did we get last time? We had the integral test. We had the direct comparison test, right? We had the p series, right? What was p series? We had sum 1 over n to the p, n equals 1 to infinity, does what? This converges for p less than 1. I'm sorry, that's exactly backwards. If p is greater than 1, and it diverges for p less than or equal to 1. In fact, p equals to 1, that dividing line, is the harmonic series. If you've been paying attention this week, it's kind of hard to miss me saying that. Like, it's starting to get insulting at this point, right? So I'm going to stop. Now, one of you asked me right before class, what if I throw away a couple terms from the harmonic series? Like, what if I throw out the 1? Is it still divergent, So one of the theorems that, I don't know if it really has a name, but you might call it the Tails theorem or something. I mean, here's a theorem I don't want to prove, but I'll state for you. The convergence or divergence of a series is governed by its tail. And so what I mean by that is it doesn't really matter. You can go all the way out to whatever. You pick your favorite finite number n, and so this piece is what I would call the tail. You could call it the, I mean, maybe you could come up with a, I mean, we could do this, right? So if we had the sum, I mean, we could write this, sum n equals, say, 1 to infinity of a sub n. We could write it like this. This would be the sum n equals 1 to n naught of a sub n plus the sum n equals n naught plus 1 to infinity of a sub n. In fact, we have a name. Oh, I think I'm about to prove the theorem. I'm sorry. I seem to have stumbled into a proof. But this piece, we have a name. We've defined this thing before. This is the S sub n naught, right? This is the n sub naught partial sum, right? That's just the sum of the first n naught term up to the a sub n naught in the summation, right? And this I never gave a name to this, but you could call this the remainder, the n naught remainder, or maybe I should say, I mean, maybe I should probably use t to call it the tail. I mean, it's the tail. It's everything else. So if the series is summable, what has to happen to the tail as n naught? I mean, as n naught goes to infinity, the tail has to it has to get smaller. It has to vanish, really. But if you fix n naught, I mean, suppose you just fix n naught at a specific value, then if you look at it, you have the tail, and then you've got the first n naught terms, right? So the first n naught terms, they're a number. Whatever they are. Whether this thing converges or diverges is completely governed by the infinite piece of it, you know? If this converges, then the whole thing converges. If this diverges, it doesn't matter if this is 17.3. 17.3 plus infinity, still infinity, right? So you can pick any tail you like, and if you can show that that tail converges or diverges, then you've shown convergence or divergence for the series. Which goes back to your question, which was, can I throw the 1 out of here? Does that change anything? No. I mean, if it converged, it would change. It would change the sum of the series, right? Like, for example, p equals 2 is kind of an interesting one. Let's look at that for just a minute. Sum n equals 1 to infinity of 1 over n squared. What's that equal to? 1 plus a fourth, right? Plus a ninth, plus a 25th, plus a 36th, plus a, what is it? I can't do 49th. I think we've done enough, right? So what's that converge to? Well, we know it converges, right? Could we come up with an estimate? If you think about the integral test, we could actually gain something from the integral test that I didn't write down last class. And I probably should actually take a second to talk about that estimate. So let's draw the picture. You know, you got this function, right? Here's my y equals f of x. Positive, decreasing, right? What else do we need? Oh, continuous, right? On 1 to infinity, so I can apply the integral test. And then we could picture, right? We can picture the nth partial sum here, can't we? So this would, for example, be S3, right? The green boxes would be S3. That would be, you know, A1 plus A2 plus A3, right? If I'm supposing that I'm assuming that we're looking at the function which matches up with some given series. So I'm saying like f of n is equal to a sub n, you know. So that picture would be a picture of S3. What would another picture of S3 we could draw, which would be above the graph, would be what? Well, I'm still S3, so I'm just saying it's a different picture, but the same boxes. We just take the boxes and like shift them this way, right? This would also be a picture of S3, right? So how is S3 related to the area under the graph? Yeah, well, we need to, I'm trying to pick something explicit to say here. Let's talk about, let's pick a target here. Let's talk about the integral from 1 maybe to what? 1, 2, 3, yeah? So the integral from 1 to 3 f of x dx, can you guys, let's relate that. What's that? Between
0 and 4? Or 0 and infinity? No, not 0 and infinity, but...
Let me shade it in here for just a... So that blue area, it's those two red boxes, right? What would those be? This is A1, this is A2, right? The green boxes are also A1, but they're not the same one. I mean, this one's A1. So I would point out that it's less than S2. Did you guys see that? Because A1 plus A2 is S2. What's it greater than?
Wouldn't it be greater than the S2 under the curve?
I don't know. I mean, that's shifted over here. I mean, directly, just looking at it, it's, let me draw it in the green so you can see it better. This is A2, right? And this is A3 over here. So it would be, you know, A2 plus A3, right? I should try to rewrite that in terms of the sum, though. What is that equal to? S3, very good, minus what? Minus A1, right? It's just missing A1. But if you can do this for 3, you can do it for n, right? So you just generalize basically the same picture. Extrapolating, we have that the nth partial, or let's say the n plus 1th partial sum, I'll say nth partial sum, n partial sum minus a sub 1 is less than or equal to the integral from 1 to n of f of x dx is less than or equal to s sub n plus 1. We have this estimate. You're right, that should be minus 1. Thank you very much. Very much appreciated. So can we estimate the p equals 2 series? Like, can we put bounds on it? What's the integral? What's the integral from 1 to infinity of dx over x squared? Equal to what? Uh-oh. Look at this. Sorry about that. My engineering notation showing limit as t goes to infinity. I mean, this notation should be understood in terms of this limiting process, right? Anyway, the point is that that's 1. So what does that tell us? Or if I just do it to n, I'm sorry, I wanted to do it to n. I'm an idiot. Dx over x squared. We got minus 1 over, well, 1 minus 1 over n, right? So apparently we have 1 minus 1 over n less than or equal to what? Summation n equals 1 to, oh, that's a bad choice of, I got to do something other than n for my variable. Say j equals 1 to, I've used n in a different way here. J equals 1 to n minus 1 of 1 over j squared, right? And over here we have what? the sum j equals 1 to n of 1 over j squared, and then minus a1. What's a1 here? But what's a1 for the p equals 2 series? What's the first term in the p equals 2 series? It's 1, right? What happens as n goes to infinity here? Looks to me like the sum, let's see here, n, well, I'll use j. So we have sum j equals 1 to infinity of 1 over j squared, right? So if we add 2 across here, is less than or equal to 2. Well, fine, let me just, here. Just focus on this piece right here. What happens as n goes to infinity? Just focus on that. We get what? We get this, the p equals 2 series, right? Written with j instead of n, oh well. Minus 1, that's 1 is 1, whatever it is, right? I mean, well, 1 is 1. We can agree about that, I think. Did they taught you in high school that yet?
No.
1 is 1?
1 is 2.
No? They didn't tell you 1 is 2? No? I mean, it's not a joke in some sense. I had a professor friend here who asked on a test once, he said, something like x is equal to 5, what is x? And like everyone just left it blank. It's like, you just wanted them to write down, x is 5. Didn't go well. Anyway, so this, you have that? Well, now that I've told you, I can't. Now that I've told you that, I can't. But of course, this, I mean, what's the limit of that? As n goes to infinity, this is 1, right? So this is the sometimes this is called the estimate. This thing I wrote down right here. This is the sometimes called the integral test estimate. It gives us a way of bounding the, even if we can't calculate the series directly, we can at least put a bound on its sum. We can tell kind of close to where it goes, right? And what this shows me, if you add 1 to both sides here, what does this give us? It gives us that the p equals 2 series, right, which I'm writing with j at the moment, is less than or equal to 2. Of course, you also know that it's larger than 0. That's not terribly surprising, but. And from just looking at the p equals 2 series, you can tell fairly fast here that it's what? Larger than 1.25. This gets you up to about what? 1.34-ish, 1.349-ish, 1.42-ish. And it gets, I know, it's harder for me to do the arithmetic in here, but it's adding smaller and smaller terms, and this says those additions can't get past 2. Yeah.
So what happened with the right side of that inequality?
Oh, I didn't use it. I didn't need it, no. I mean, I could use it for something, I imagine, but by the way, this is actually kind of an important point for me to make. Is this any different than the n equals the p? Is this the p equals 2 series? This is the p equals 2 series. See, this is another thing I haven't talked enough about in here yet. But n equals 1 to infinity of a sub n is equal to the sum Pac-Man equals 1 to infinity of a sub Pac-Man. I mean, it doesn't matter what you use for your your index of summation, it's the same sum operationally. So do you guys want to guess? Yeah.
So like on a test, if you gave us like a p-series, you used pull us to, or are you going to ask us what it converges to?
I could ask you to estimate what it converges to.
Gotcha.
I could say use the integral test estimate to give a bound on, I mean, to estimate what the p equals whatever series converges to, or some other series, right? That would assume, of course, that the integral is manageable. Now, this one happens to be known. This is a famous result due to Euler a while ago. I can work this out with Fourier series. Maybe I'll show it to you guys at the end of the class or something. But this works out to pi squared over 6. So we figured out, I think we got up to about 1.5-ish in my back of the envelope calculation. What's pi squared over 6? Can somebody tell me that? Yeah, please, radian. Well, it's pi.
So 1.64 radians.
1.64. Yeah. So even through just adding up these, through adding these up, I was actually able to do better than just saying it's lower than 2, right? Through the short calculation I did, I was actually able to say that basically 1.5 is less than, it's between 1.5 and 2. If you look at what I just argued, that's really, I had that much. And I could do better, right? I could keep adding terms, and I could keep showing that it gets closer and closer to that. But to actually prove that it's pi squared over 6, that's tough. We don't really have the tools in here for that at the moment, truthfully. It's easy for us to show it converges. To actually find what it converges to is a much harder task. Okay? Let's talk more about geometric series. Because I keep hitting geometric series at the very end of class, and we should actually spend some significant time on geometric series. They're important. So some examples of geometric series. So definition, just to remind you, geometric series has form A plus AR plus AR squared plus AR cubed plus dot, 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 dot. In other words, we can write it, the summation n equals 0 to infinity of AR to the n, right? And we say R is the ratio of the series. I'm not sure how standard that terminology is. I just want to give it a label. All right? That's not a bad label for it, and I'll explain more in a second why that is. Our theorem was simply this, that the geometric series A plus AR plus dot, 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 it equals to A over 1 minus R if and only if, if the absolute value of R is less than 1 and it diverges for radius. Oh, radius. It's the radius. I'm an idiot. Radius. Or is it the ratio? I don't know. For R, I know it's annoying, greater than or equal to 1. Tell you what, I will try to do some research on the proper term. I have trouble making decisions like this. Rest assured, I will not take off points if you call it radius or ratio. Okay? And I probably won't take off points if you don't call it anything, but it's nice to have a name for it. Name calling is important. If there's anything we've learned in the last year or so, it's that. But, sorry, comments. Yes. So example. So what if we have, let's say, the sum n equals 0 to infinity of 2 times 1/3 to the n times 3 to the 2n. This is a series. We can try to decide whether it converges or diverges. Oh, this is dumb. Sorry, let me fix that. This is supposed to be 7. And that was supposed to be a minus. There we go. Now it's more exciting. All right, so if you look at, so just a comment, right? So if it's geometric, right, what does that mean? Has a sub n equal to what? What's the nth term in this geometric series? There's a formula, right? A times r to the n. So if we take a sub n plus 1, right? If we take a sub n plus 1 and we divide by a sub n for a geometric series, what's that look like? That's a r to the n plus 1 divided by a r to the n. What happens? If we take the ratio of any two subsequent terms in a geometric series, we should just get back r again. If that doesn't happen, it's not geometric. So this comment you could also look at as the geometric series test. This is the geometric series test. If you can take the ratio of two subsequent terms and get it constant, well, that constant's the ratio, or the radius, and it's geometric. So is this a geometric series, right? We can figure that out by looking at this as being a sub n, right? And we can look at a sub n plus 1 divided by a sub n. What's that going to be? So here's where not knowing laws of exponents is going to hurt you. But you guys know laws of exponents by now, right? Sure you do. I think you do. That pesky Euler, he did everything. So annoying. That results from like the 1730s or something stupid. So the 2's cancel, right? 2 cancels. And what do we got? It looks like we got ourselves 1/3, right? Because we have 1/3 to the n plus 1 divided by 1/3 to the n. And we got 7 to the what? Minus 2n minus 2 plus 2n. So I distributed the minus 2 upstairs. That gave me the minus 2n minus 2. If I have a reciprocal, minus 2n power, when I bring that upstairs, it becomes plus 2n, right? So those cancel. And it looks like we've got 1/3 times 7 to the minus 2, also known as 1 over, what? 3 times 49, aka 147. So the ratio here is 147. Oh, it's geometric, right? That shows it's geometric. And also, bonus, we can see that it's convergent, right? What does it converge to? What's the sum of the series? So I mean, I can actually rewrite this just to be explicit. It's a good practice to do this as well. You know, this is 2 times what? 1 over 3 to the n times 7 to the minus 2 to the n, right? And so that's why, by direct laws of exponents, you can see as well that it's geometric, right? Because this is 2 times 1 over 3 times 7 to the minus 2 to the n. So you can just, by this direct algebra, once you get the series into this form, you can compare with the standard geometric series and say, aha, if it looks like a duck and it walks like a duck and it has the right form of a geometric series, it's a geometric series. So, I mean, it's the right pattern, right? And you can see that the thing inside the parentheses must be the ratio. Or the radius, yeah. So what does it converge to? What's the sum of the series? So what's A? A is equal to what here? 2? 2 over 1 minus 1 over 147, which I recommend multiplying by 147. So that's 2 times 147 divided by, what's that? 146, yeah. So yeah, okay, that. So very close to 2. A little bit bigger than 2 is the answer. You got a calculator, you can tell me exactly what it is, but I don't really care. I mean, this could be simplified a little bit, fine. But any questions? Yeah.
I'm going back here. Why do we put 2 over 1 subtract 1?
Oh, this is the theorem. It converges to A over 1 minus r, provided the radius is appropriate. You guys started to ask me about, what are the rules for combining series? And I really should prove these for you guys one of these days, but I don't. Jerry's doing a flyover? Oh, is it Trump? Trump heard CFA was in town. He's like, I'm going to come and help Jerry out. It's going to be huge. So you guys heard the joke about Tim Tebow finally getting his way? Everybody's taking a knee. Yes. So you guys are not on the same Facebook circles as my wife, apparently. It's not my joke. Is that a sports joke? I think it's a.
No, that was good.
Well, I told you guys before, this whole taking anything gives me hope. It says to me that football will be depopularized in my lifetime. Death of football is nigh. But my friend Paul, he said, Crazy Paul, as we talk about sometimes, he's like, but there's still hockey and baseball and other things, and people will just flock to those. And I said, that's fine. I just need 1 or 2 players to start making a political statement in those, and then they'll fall down too. So, just a matter of time.
Do you like any sport?
No.
Math or sport?
I think that, well, anyway, I think a lot of things. So here, example 4. How about this? What if you had the sum n equals 0 to infinity of 1 over n plus 1 quantity squared plus, I know. I don't know, like 7 to the n plus 1 over 10 to the 2n. Now here we need a theorem that I haven't stated yet, and that theorem states that you can break a series up into a sum of series provided that your subsequent, after you break up, you're still convergent, So you could call this is like the parent, and these are the children. So you can only, all right, it doesn't concern us. So your n equals 0 to infinity. So in order to do this, I must know that what I'm writing on the right-hand side here actually converge. So technically speaking, I'm taking out what I like to call a logical loan. This is only valid after I actually demonstrate that these 2 series that I just wrote, in fact, separately and independently converge. They do. So what's this? This actually gives me a chance to illustrate something else. This is actually the sum j equals 1 to infinity of what? Make j equals n plus 1, right? Make a substitution, j equals n plus 1, then n equals 0, it says j equals to 1, right? And just what you said, it's 1 over j squared. Yeah, so this is actually the p equals 2 series, which we know, in fact, converges, right? And in fact, to pi squared over 6, but whatever. And plus this piece over here. What's this thing, though? See, what this is this is 7 times 7 over 100 to the n. Exactly what? So 7 to the n plus 1 is 7 to the n times 7, right? Or let's say 7 times 7 to the n. On the other hand, 10 to the 2n is what? This is 10 to the 2 to the n, also known as 100 to the n. So you put both of these facts together, and the fact that, you know, a to the n over b to the n is a over b to the n, that leaves the 7 out here and the 7 over 100 left, right? So you can identify this is a geometric series, right? Geometric with a equals to 7 and r equals to 7 over 100. So in fact, if you accept that pi squared over 6 is known, we can actually calculate the sum of that series. It's pi squared over 6 plus 7 over 1 minus 7 over 100, which of course we could simplify. That's pi squared over 6 plus 700 divided by 93. Yeah? Because the radius r was less in magnitude than 1.
How about you can only tell if it's divergent or it's convergent?
I can, geometric series is really nice because it tells you convergence and divergence. Once you know something's geometric, you own it. It cannot escape your logical grasp. It's like a quadratic equation. Once you see something's quadratic, you can solve it. There's no exceptional case. Geometric, we know convergent and diverging. Not only do we know if it converges, we know what it converges to. So like geometric series is the holy grail of series, indeed, yes. And you know, guys, as you go on in math, what you'll see, if you do, is that the geometric series appears in the heart of many important and technical central theorems of mathematics. Like many of the deeper theorems in math basically start with an application of the geometric series. It's really, really important, actually. Yeah.
So the p equals 2 series will always go to pi squared over 6?
Yeah, yeah. Yeah, once we know what a series goes to, it doesn't stable. Like it's not going to. I mean, that's actually a very challenging question. Like, is there some sort of alternate mathematics I could think of where the p series would go to something else? And how would that work? P equals 2 series will go to pi squared over 6 forever and ever in regular calculus classes. Yeah. So it works for us. Now I have I've tried to focus today, guys, on examples where we can actually calculate the sum of the series. Last time I showed you the other type of example, which was the telescoping, right? So the next, like, we have this thing called the weekend, yay! And then we'll come back, and then we'll do more divergence and convergence tests. There are still a few left. We still need to talk about limit comparison. We still need to talk about ratio and root tests. These are important things. And once we have everything, then we can just try to, face a wild series and try to say, does it converge or diverge? We're getting there. But it's really important to know. In some sense, geometric series is a test of its own. If you can recognize a series as being geometric, game over. I mean, you know what happens. If I ask you to calculate the sum of the series, and I usually say something a little bit more wishy-washy, like determine if the series converges or diverges. If possible, find its sum. So, if possible, find its sum. Like, what are the ones that it's possible to find the sum for? It's pretty much either geometric. Oh, yeah, first of all, it has to be convergent, but that alone is not enough. P equals 2 series is convergent. Can you find its sum? Not unless I tell you that it's pi squared over 6, right? So that's just Trivial Pursuit. I don't expect you to memorize pi squared over 6 or anything like that. I'm telling you for your own informational purposes. I'm not expecting you to remember that and memorize it or anything like that. I do expect you to memorize and take ownership of the geometric series theorem, because that is the main class of examples that we can actually calculate sum of. There's a larger question, though, like why are we doing this? Like, why do we care about convergence and divergence? Why do we have to be careful? And so I'd like to show you a cautionary tale to end this week's lectures. I want to show you, this is an example I think is kind of interesting. So imagine you're taking a trip and you go 3 units this way, right? And you go 4 units that way, right? Right? But then imagine you break it up and you change it to a stair step. So instead of doing that, you go like this, like halfway, and then you go up 2, and then like that, right? So how far have you gone? You've still gone 3. So like, you know, what's the distance traveled along the black path versus the blue path? So the blue path has length 7, right? The black path still length 7, right? Okay, so divide again. Still, I'm just taking purely horizontal and purely vertical paths despite the limitations of my drawing. Imagine those purely vertical and purely horizontal. Still length what? 7. Okay. So keep doing this, right? Keep doing this until you get to I can't do a very good job drawing it, but you get what I'm saying. Here, I'll just draw it like that. It's not quite right, but what I mean is that if you could zoom in on that, it would still be stair-stepping, right? So what's the length of the blue stairs? 7. But isn't that length square root of 5? I mean, square root of 9 plus 16 is that length is 5. Isn't this a good approximation to that line segment? It's infinitely close to it as the stair steps get infinitely small, right? It's right on top of that hypotenuse.
Is it square root of 5 or square root of 25?
I think it's square.
Oh, sorry, I'm an idiot. I've ruined it. Yes, 5. Square root of 25. So how is it? So apparently 5 is equal to 7, right? Or you could, or 3 squared plus 4 squared is not equal to 5 squared. Or the Pythagorean theorem is wrong. What's wrong? See, precision matters because it can lead you astray if you accept fuzzy notions. Through fuzzy arguments, I just made you doubt the Pythagorean theorem. Should I explain what's wrong with the argument?
I mean, is it ever? It wouldn't.
How do we, I mean, the point is you can't calculate the length of this infinitely jagged curve is not given by the length of the line. I mean, you can't define length for the infinitely jagged stair-steppy curve, basically, is what it is.
If you use trapezoids,
It's not a smooth curve. It's, in fact, a very, very unsmooth curve, this finely stair-stepping thing. And yet, it seems like in the limit, right, in the limit of the infinite number of stair steps, it seems like it's just the line segment, right? So there's something wrong about passing to that limit.
So,
All right, well, have a nice weekend.